Math 1314, Section IC1, Spring 2022, Tyler Junior College, Section 4.3, Rational Equations. Video 2, Solving Rational Equations, Type 1. What do I mean by Type 1? Well, by Type 1, I mean rational equations whose denominators are monomials. And by monomial, I mean a single term. For example, x by itself is a monomial, as is 7. 2x is a monomial. In fact, all these numerators are also monomials. The mono in monomial means 1. Now, what's an example of something that's not a monomial? Well, a binomial like 2x plus 5, which has 2 terms, or a trinomial like x squared minus 3x plus 2, which has 3 terms. The binomial is made up of 2 monomials, and the trinomial is made up of 3 monomials. In general, though, a monomial is just a product, multiplication problem, of numbers and or variables. But when you add them together, then you start getting polynomials. All right, so we're going to solve these, but how are we going to solve these? This isn't a skill that's new. This is a skill that we've seen already when we were solving different types of inequalities and even some simple linear equations. When we were solving equations, excuse me, and inequalities in the past, our strategy was to get rid of the fractions by multiplying by a common denominator, excuse me. That strategy has not changed. So we're going to multiply both sides of the equation by the least common denominator. Now, it may not be obvious what the least common denominator is, but the truth is it doesn't even have to be the least common denominator. It just has to be a common denominator capable of canceling all of the fractions. We've canceled fractions before, but I want to remind you how this is going to go. I'm going to start by setting up a parentheses around both sides of the equation. Now, I'm going to multiply something on both sides, but if either side has more than one term, the left side does, it's going to get distributed to each term. So I'm going to be proactive about it and go ahead and get ready to distribute across the addition on the left. Now, if you don't know what to multiply by, here's a strategy. We are trying to cancel the denominators so that we don't have a fraction anymore. To cancel that, we have to multiply by something that matches it. So in the first fraction, whose denominator is x, we must multiply it by at least an x in order to cancel that denominator. But we have to multiply everybody by the same thing. So everybody is going to get multiplied by an x, and that will set up a cancellation in the first fraction. In the second fraction, we need to cancel a 7, which means we need to multiply by a 7. So everybody's going to get multiplied by a 7. But what do we need to cancel in the third fraction that has a 2x on the bottom? Now, if you're thinking we need to bring in a 2x, that wouldn't be wrong, but you want to be careful not to multiply by any more than necessary. We've already got an x set up to cancel. Remember, the rule for canceling in a fraction is you can cancel matching parts of multiplication problems, one on top, one on bottom. Since 7x means 7 times x and 2x means 2 times x, the x's are eligible to cancel, so we already have enough ammunition to cancel the x's. What we don't have is something to cancel the 2. So we are going to bring in a 2 as part of our multiplier. Now, you could figure out all this on the side. I have to hit everybody with a 7, an x. I have to hit everybody with a 7. I have to hit everybody with a 2. And then multiply it all together to get 14x, that would actually be your least common denominator. And there's nothing wrong with identifying that first and saying, all right, everybody's going to get hit with the 14x because 14x has enough factors to cancel everything. But regardless of whether you set up your multiplier piece by piece in the equation or to the side and hit everybody with the same thing at once, you should be able to cancel all the fractions. In this problem, on the first fraction, on each fraction, we're going to cancel and multiply what's left. On the first fraction, the x's cancel, and that leaves us 14 times 3. 14 times 3 is 42, but I realize I do not have enough room for everything. So give me 1 second to pause and relocate things. There we go. And I put a cloud, a thought cloud, if you will, over where I calculated the 14x. But we were in the midst of multiplying, canceling, and gathering what's left. On the first fraction, we multiplied by 14x, canceled the x's. That leaves 14 times 3. 14 times 3 is 42. Plus, on the second fraction, we don't have a 7 to match, but the 7 divides into the 14. Remember, fractions are just division problems. So this says 14 divided by 7, whose answer is 2. And that leaves a 2, an x, which we didn't cancel, and a 5, all getting multiplied. Together, that multiplies to give 10x. And on the third fraction, we have two things to cancel. 14 divided by 2 leaves a 7, and the x's cancel. That leaves 9 times 7, which is 63. Now we haven't solved the equation, but I think we'll all agree it's better than it used to be, because now instead of having 3 fractions, it has none. This is a basic linear equation. We can finish it by subtracting 42 from both sides. Cancel the 42s on the left, leaving 10x on the left, equals. On the right side, 63 minus 42 is 21. And of course, our last move would be to divide by 10, which I'm not going to manually write because it's kind of crowded down there. But we do get x equals 21 over 10. Now, before we say, ta-da, the problem is over, I owe you guys an apology. There's something I meant to do at the very beginning, and I will do it on the next one. It's an easy something to forget. When you're solving a rational equation, remember what we did in the first video? You have to determine the restrictions. Well, you don't have to, but you should. Let me get rid of my image. And while I'm at it, I'll take this down a font size. Maybe. Okay. When you solve a rational equation, you should determine the restrictions, because if you get one of those as a solution, you have to throw it out. In this particular equation, there's only one restriction, because the only variable in the denominator occurs in the first and third fractions. But if you put both of those equal to 0 and solve them, you'll get the same thing. X is equal to 0. We can't have x equal to 0 in this particular equation. And so the restrictions at the very beginning should have said x is not equal to 0. I'm going to draw the line through the equal sign. X is not, oh, that's a yellow line. How'd that get yellow? X is not equal to 0. I can do better than that. Hold on. X is not equal to 0. And again, it's not catastrophic on some problems if you do not determine the restrictions. However, it can be on others. So I didn't mean to do that. So when you're solving a rational equation, you might want to stop and ask yourself, what can I not get for a solution? Because if you do, at the end, you have to throw it away. And don't worry, sometime between now and the last video, that will be an issue. Let's take a look at another example. Solve 1 plus 8 over x squared is equal to 6 over x. Well, it should be pretty evident that x cannot equal 0 in this one either, because we don't want a denominator to be 0. And both of our denominators would be 0 if x was equal to 0. All right, so how are we going to solve this? Well, same way we solved the last one. I invite you to pause the video and try it, but I'm about to jump into it right now. And I'm going to bring a picture back. Gives a little bit more personality to the video, I think. All right, we're going to multiply all the terms of the equation by something capable of canceling all 3 fractions. Do you know what that something is? What can I multiply that will cancel both an x squared and an x? Now, if you're thinking an x squared and an x together to give you an x cubed, that would get the job done, but it's also going to create a 3rd degree equation, which we're not ready to solve yet because that's what would show up over here. This is why you want to try to use the least common denominator. Now, when it comes to multiplying to cancel powers of a letter, the least common denominator, ironically, is the x with the greatest power. Let me say that again. When you're multiplying to cancel powers of a letter, like x and x squared, the least common denominator is the letter with the highest power. Sounds backwards. We're going to multiply everything by x squared. It makes sense if you think about it, because our goal is to cancel all the fractions. If I were to use the lesser power, it would not cancel the x squared in the bottom of the middle term. All right, let's see what happens. Well, nothing happens on the front end because it just says x squared times 1, which is x squared. Plus, in the middle, the x squareds cancel, and that leaves an 8. Equals. Now, on the right side, you got to be a little bit more careful because x squared means x times x. So one of those x's will cancel, but one will remain. 2 x's cross out one of them, leaves 1 x. That leaves a 6 and an x. Well, looky what we have here. Sorry, I was channeling Biff Tannen from Back to the Future, the original one. Well, looky what we have here. We have a quadratic equation that I just moved up a little bit to create some room. So how do we solve a quadratic equation? Well, you just had 3 homework assignments over it. In most cases, you want to get it equal to 0. This is one of those cases. So I would subtract 6x from both sides, put it in the middle, and get x squared minus 6x plus 8 is equal to 0. Now, if you want to use the quadratic formula, which I should have warned you isn't going away, you can. However, this one will factor. It will factor into x minus 2 times x minus 4. If you don't know why, I strongly recommend going back and rewatching those videos reviewing factoring techniques. But it's factored in equal to 0, which means I can split it and write x minus 2 equals 0 and x minus 4 is equal to 0, both of which are pretty easy to solve. That gives us x equals 2 and x equals 4, neither of which were the number that we had to avoid, the restriction. So in a nutshell, to solve a rational equation, your first move is to make it not a rational equation by multiplying by something capable of canceling all of the fractions. Moving forward, and keep it in mind that if you get an answer that you're not supposed to, you have to throw it out. Hasn't happened yet. Promise you it will. Let's take a look at one more. Now, this one may look a little bit more intimidating because there's 3 fractions and the numerator of one of them is a binomial. The numerator of the first one is x plus 1. But that changes nothing about the difficulty. In fact, this one's, I would argue, is easier because of focus on the denominators. Notice the denominators are all constants, 5, 6, 10. That means 2 things. Number 1, no restrictions. There's no x's in the denominator, so no value of x could accidentally make a denominator equal to 0. And number 2, when I'm multiplying, I need to think about just numbers. All right, so let's see what happens here. Now, there is a way to locate the least common denominator for a group of numbers, and it can be adapted to things that don't have, that have more than just numbers. But without making a whole new video on how to find the least common denominator, here's how it goes. You take each denominator separately, and you're going to factor them into the product of prime numbers. For example, 10 is 2 times 5. That's as far down as it can factor. 6 is 2 times 3. And 5, of course, is just 5. And the way you build your least common denominator is you take each unique factor with the highest power it may have. Now, all of these factors have a power of 1. 5 to the first power, 2 to the first, 3 to the first, 2 to the first, 5 to the first. So we really don't have to worry about grabbing each factor with its highest power. But there's a factor of 2, its highest power is 1. There's a factor of 3, its highest power is 1. And there's a factor of 5, its highest power is 1. I know the 5 shows up twice, here and here, as does the 2. But in the individual denominators, it only shows up once at a time. So I only have to worry about taking out 1 5 at any moment. 2 times 3 times 5 is 30. Now, you may have looked at this and said, I knew the common denominator was 30. Why'd you do all that? That's great, but sometimes you won't. And I wanted to give you a technique, even though I demonstrated it on a fairly small scale. Our multiplier is 30. That's going to take out all the fractions. If you multiply by something, and at the end you still have fractions, your denominator wasn't large enough. Everybody's going to get hit with a 30. And now we're going to cancel and see what's left. 5 goes into 36 times. That leaves us 6 times x plus 1. And the x plus 1 is still in parentheses. Minus, on the second fraction, 6 goes into 35 times. That leaves us 5 times 2x. I think I'm going to go ahead and multiply that and call that 10x. And on the right side of the equal sign, 10 goes into 30 3 times. 3 times 3 is 9. Now, we're not out of the woods yet, but the equation is much better than it used to be. That's the whole strategy for solving rational equations. Multiply by something that will take out all the fractions and then proceed. In this case, proceeding means distributing the 6 to eliminate the parentheses. 6 times x is 6x plus 6 times 1 is 6. We still have the minus 10x, and we still have the equal to 9. Combine like terms. Our like terms here are the 6x and the minus 10x. 6x minus 10x is negative 4x. But we still have the plus 6 equals 9. Let's move this to the next page. Negative 4x plus 6 is equal to 9. Now it's a basic linear equation. Subtract 6 from both sides to get negative 4x is equal to 3. And then divide both sides by negative 4. If you were thinking divide by positive 4 because positives and negatives are opposites, that's when you're adding and subtracting. You need positives and negatives to cancel when you're adding and subtracting. When you're dividing, you're setting up a division problem equal to 1. Negative 4 divided by negative 4 is positive 1. On the right side, we have 3 divided by negative 4. In my opinion, the negative should go in front of the fraction. It's okay if you leave it on the bottom with the 4. It's even okay if you put it up top with the 3. So yeah, type 1 rational equations are rational equations whose denominators are monomials, even if their numerators aren't. Because again, in this third one, we had a numerator that was a binomial, but we were focusing on the denominators because that's the obstacle we're trying to overcome. Oh, well, that wasn't too bad. All right, I'm looking for something. I can't find it. There it is. I was looking for the thing to stop recording the video.